So we're going to look at now other coordinate representations. In other words, other ways to think of representing these graphs. And I'm going to start off with this question. What is the equation of a circle when you have the radius of 1 and the center is at the origin? So what we've seen is that the equation for this is x squared plus y squared equals 1. Okay. So that's a simple equation for a simple graph, and yet it's not a function. So we know a circle is not a function. Now it turns out that there are other ways to write down a formula for the graph of a circle. And that's what we're going to be looking at here. And in fact, those techniques will let us do amazing things like, for example, we will learn the equation of this graph. And the topic for this is parametric equations. Okay. So here's a fun little graph. If we tried to mathematically describe this graph, clearly you could not write a function equation y equals f of x. It's not a function. So how would you describe a graph like this? Well, I would say in words it kind of looks like a path. You start at one point, you sort of travel around, Therefore, one way to describe it would be with a formula that gives our coordinates as we walk along a path. And we could keep track of our journey using time. After 1 minute, you're here. After 2 minutes, you're here. After 3 minutes, you're here, et cetera, et cetera. So at every time t, when you describe our location, our position has two components, x and y. Therefore, x is a function of t, and y is a function of t. Here's the notation for how you write that down. X equals f of t, and y equals g of t. And some people prefer the notation x equals x of t and y equals y of t. Either way, x and y are functions of t. Okay. So one comment, thinking of time as that variable, which we're going to call our parameter, is the most common approach. Another common approach is to use distance. For example, after I've gone 1 mile, I'm here. After I've gone 2 miles, I'm here, et cetera, et cetera. The important aspect is that you have a single variable changing, and that tracks, and that's what tracks our position in space, which in this case means where we are on the path. So what I want to talk about now is how do we think of graphs that have equations like this? So what can we do? So here is such an equation. X equals t squared and y equals t plus 1. So how do you graph this? What can you do?
We start with t equals to 0 and then infinity and put in x and y.
Yeah. So go back to basics. How did we learn to make graphs? Right? So t equals 0, 1, 2, 3, 4, blah, blah, blah. What are our x and y values? So when t is 0, x is 0, y is 1. When t is 1, x is 1, y is 2. When t is 2, x is 4, y is 3. When t is 3, x is 9, y is 4, et cetera, et cetera. So now we have stuff that we can graph. So we know that our graph has the following points. Here, 0, 1, 1, 2, 4, 3, 9, 4, etc. So we know that this is the point, for example, 0, 1, and then this was, 1, 2, 4, 3, 9, 4. And this is a pretty simple, these are simple equations, so we know that the graph is just going to kind of run like that, a curving line. So that's what the graph looks like. And again, this point occurs, let me not do that. This point occurs at t equals 0. This next point occurs at t equals 1. This point occurs at t equals 2. This point occurs at t equals 3. So that's the path that we're walking down, and that's how time elapses as we're going down that path. So absolutely, let's not think that you can only have positive numbers. -1, -2. When t is -1, x is 1, y is 0. When t is -2, x is 4, y is -1. Let's fill in those points. So 1, 0 would be right there. 4, -1 would be right there. So the path also is going to continue that way. And that point is when t equals -2. So et cetera, et cetera. Okay. So let's do another example. Okay. Whoa. Okay. So again, do the same thing. We get t value and x and y. So let's choose a bunch of t values, 0, 1, 2, 3. So when t equals 0, x is 0, y is 1. When t equals 1, x is 4, y is 3. When t equals 2, x is 16, and y is 5. Numbers are starting to get big, so I'll just leave it there. Okay, so now let's graph it. So at 0, you have 0, 1. Then you have 4, 3. Then you have 16, 5. So what does this graph look like? It looks like that. So let me fill in one more point just to make a point. So what about when t equals -1? X is 4, and y is -1. So we've got 4, -1, so we've got that point. So what do you think? So what do you think about these results? We have what we need. So what do you think? What do you think about these graphs? This graph and this graph. And if it's not clear, hold on one sec. Sorry, I've said too much. There we go. Okay. So remember, this was 0, 1. This one was 4, 3. This one was 16, 5. And this one was 4, -1. So in fact, what you can see is that these are actually the same graph. As they appear on the x and y axes, these are the same graph. They were not the same equations, though. So what happened?
Basically moves in time a lot 4 times faster. So when we plot
Almost. Different equations can have the same graph. What changed was the velocity at which they're traveling along the graph. Because notice that the x and y values got bigger much quicker in the second one. So why did that happen? So Each set of equations is called a parametrization of the graph, and changing from one to another, so t is called the parameter, and changing from one to another is called a reparametrization. So in this example, how did we reparametrize? We replaced t with 2t. So look at the equations again. Come on. Okay. So in the first equation, it's easiest when you look at y. Y was t plus 1, now y is 2t plus 1. In the first one, x was t squared. Replace t with 2t, you get 4t squared. So all we did was we changed the parameter in some way. So we replaced t with 2t, and you get these new equations. So what that means is that you're going to get the same xy points, but they're going to occur at different values of t. So if you like, you get there in different times. So your speed is changed, is one way to think about it. So now let's make this graph. What is the graph of x equals cos t, y equals sine t? Okay. So we need t, x, y. Now because we've got trig functions, I'm obviously not going to be plugging in t equals 0, 1, 2, 3. We're going to plug in easy, right? We're going to plug in easy things that we know. So let me start at 0. So x, when it's cos t, it's 1, sine t is 0. So what's another nice one that we know? Pi over
Or pi over 4.
Pi over 2 is an easy one, yes, but I'm going to want to fill in some intermediate values. So I'm going to go pi over 6, pi over 4, pi over 3, pi over 2. Okay. So pi over 6, cosine t is root 3 over 2, and sine of pi over 6 is 1/2. Okay? Then for pi over 4, cosine t is root 2 over 2, sine t is root 2 over 2. Those are a little small. Okay. Then for pi over 3, cosine is 1/2, and sine is root 3 over 2. And then for pi over 2, cosine is 0, and sine is 1. So we could keep going, but I think these points will give us a good idea. Let's make the graph. When t equals 0, we're at the point 1, 0. When t equals pi over 6, x is root 3 over 2. That's approximately 0.85-ish. And y is 1/2. So that takes us right about there, approximately. Okay? Next, when t equals pi over 4, x is root 2 over 2, and y is root 2 over 2. And that's approximately 0.7. How am I doing here? I'm doing so-so. All right. That's when t equals pi over 4. Next, we have at pi over 3, we have 1/2 and maybe something like that. Okay. My drawing skills notwithstanding, get this. Okay. So it should look something like that. Okay. So what do you think it is that I'm supposed to be drawing? This should be a circle, right? So if I could draw, we now have a perfect quarter circle. So guess what happens as t values keep going? Right. And what do you think the t value is going to have to go to in order to draw an entire circle? Right. So you may be used to thinking in degrees. That's going to have to convert to radians right now, because we're always going to work in radians. So if we keep going to 2 pi, you're going to be back. You're going to have completed the journey. and we'll have the unit circle. What happens if t keeps increasing after 2 pi? You just keep going around the circle more. Exactly. So it's true that sine squared of t, well, starting from x squared plus y squared equals 1. Make sure I get x and y correct here. So cosine squared t plus sine squared t equals 1. But with parametrizations, there's a tricky little thing. So here's a sort of more advanced idea. We could also do this not just with t, but we just saw we can have reparametrizations. We could do this with 2t. So cosine squared of 2t plus sine squared of 2t also equals 1. Now, what effect do you think that's going to have? We're going to go around the circle faster. Exactly. So when will we complete one loop around the circle? When t equals what? When t equals pi. Exactly. Does that make sense? Okay. So once again, there's this issue of reparametrization, which is an issue sometimes we need to think about it. Okay. So what if you have just a regular function y equals f of x? You can still use the idea of parametric equations. You can simply say that x equals t and y equals f of t. But you also have this flexibility. What if x is a function of y? Well, then you can say y equals t and x equals g of t. So the idea of parametric equations is actually a very powerful one. Parametric equations are one way to generalize the idea of a function. So even if you don't have x as a function of y, even if you don't have y as a function of x, you could still use function notation to write your equation down for some situation or for some graph. That's the basic idea behind parametric equations. And now we're going to learn to do calculus with parametric equations. Okay. So here's the general comment. Previously, you learned all of calculus using an xy coordinate system. Okay, everything that you learned can now be situated using parametric equations. So let's take a look. First of all, calculating derivatives. So you want to find the derivative, which is the slope of a curve. Okay, this is possible because what does a derivative mean? It means at any point on a graph, when you zoom in, you're going to see a straight line. Now, in parametric equations, we can't, the idea still holds, right? Even if you have some graph that's not a function, like a circle, you can still zoom in at a point and you're going to see a straight line. Even on a super crazy graph like that, when you zoom in, you're still going to see a straight line, as long as there's no corner. Okay? But how do you calculate it? You can't calculate it in the usual way because we're not starting with y equals f of x, but we're starting with x equals x of t and y equals y of t. Okay. So how are we going to find this? The way we're going to find it is we're going to say that y is a function of x and x is a function of t. So let's take a look at what happens. So I'm going to write y as a function of x, so y equals y of x. But that really just means y, which we really know is y of t, is a function of x, which is a function of t. So y of t equals y of x of t. Just take the derivative of both sides. Now when you take the derivative, what's our variable? Our variable is t. Right? Because in parametric equations, your variable is t. So we're going to take the derivative with the variable being t. So d dt. So what happens? Well, if you have y of t, derivative with respect to t is just dy dt. Okay, what happens on the right side? On the right side, you have to use the chain rule because it's a function of a function. Y is a function of x, x is a function of t. So when you chain on that, what you get is y prime, but that's dy dx, and then x prime, which is dx dt. So that equation, so not only does it come from the chain rule, it should quote unquote make sense if you cancel the dx part. And so now we can simply solve for what is dy dx. So dy dx is dy dt divided by dx dt. So on the one hand, this should kind of make sense because you're like, oh, dy dt over dx dt, if you just quote unquote cancel the dt's, you just get dy dx. On the other hand, we don't typically think of dt as something that you can cancel, so dy dt has its own meaning and dx dt has its own meaning. So how to link those ideas up is a long discussion, which I'm not going to get into right now, but this gives you an idea of what we're doing. So note that if dx dt equals 0, this expression is undefined because it's in the denominator. Okay. And here's a description of how you find the second derivative. Now notice, notice that dy dx is dy dt over dx dt. The second derivative is not second derivative of y over the second derivative of x. That's not true. So we have to show what the second derivative is by simply taking the first derivative and taking the derivative again. So the second derivative of y with respect to x is simply dy dx, but then take ddx of that. So it's ddx of the original thing, but we know how to take ddx. We saw that dy dx is just dy dt over dx dt. So ddx of dy dx is just d that dt over dx dt. It's one thing inside another thing. You just have to do it a second time. So let me just diagram that right quick. Notice that d blah dx equals d blah dt over dx dt. That was the thing that we just found. Only now, instead of saying do that for y, now we're doing that for dy dx. So now ddx of this is ddt of this over dx dt. In other words, instead of having y, I've replaced y with dy dx. So that's how we made a second derivative. Okay. Oops. And just for your entertainment, shall we say, here is a proof of the derivative formula actually using limits. Okay. So let's take one moment to just calculate one derivative. So for the curve x equals t squared and y equals t cubed minus 3t, let's find the slope of the tangent when t equals 2. So the slope of the tangent just means, what do we have to calculate? That means we have to find the derivative. So we need dy dx. So A. So dy dx, as we said, is dy dt over dx dt. So what is dy dt? It's 3t squared minus 3, and dx dt is 2t. So there's the expression for dy dx. Now the thing we're being asked is, find the slope of the tangent when t equals 2. So when t equals 2, dy dx equals 3, 2 squared minus 3 over 2 times 2. So this winds up being 9 over 4. So that's the slope. That's the slope of the tangent line.
When t equals 2.
When t equals 2, exactly.